Hey everybody, my name is Chris and I'm a tutor here at Chegg.com. I mostly do math and computer science, and in this video I would like to talk to you a little bit about testing series for divergence. So we're only going to talk about a few of the tests, and the first one that we'll talk about is the Nth Term test. So this, in my opinion, is probably the most important test for divergence, and I think it's the one that you should always try first because it probably is the simplest one to use. And if you could use this right away to determine that your series diverges, then that could save you a lot of work later on. So, what's this test say? Well, it says if the limit as n goes to infinity of the sequence a sub n is not 0, then the series, the sum from n equals 1 to infinity of a sub n, diverges. Okay? And that's all the test says. So if this limit is equal to 0, or, if the limit is equal to 0, then the test is not conclusive. You don't really know one way or the other. So let's see a couple examples. Let's say we have the series, sum from n equals 1 to positive infinity of n squared. So for this particular example, our a sub n is n squared right here. Okay, so a sub n equals n squared. So what's the limit as n goes to infinity of a sub n? Well, since a sub n is n squared, this is the limit as n goes to infinity of n squared. And as n goes to infinity, where does n squared go? N squared also goes to infinity, just more quickly. But the point is it goes to infinity. So that is certainly not 0. Therefore, the limit, so we see that the limit as n goes to infinity of a sub n is not 0. So the nth term test tells us that this series diverges. Okay? So that's one example of being able to apply the nth term test. Let's look at another example, and let's see what happens if we have, let's say we want to look at the sum from n equals 1 to positive infinity of 1 over n. Well, in this case, our a sub n is 1 over n. So to apply the nth term test, we want to look at the limit as n goes to positive infinity of a sub n, which is the limit as n goes to positive infinity of 1 over n. And that actually is 0, because as n goes to infinity, 1 over n gets smaller and smaller and approaches 0. So the limit as n goes to infinity of 1 over n is in fact 0. But that's not good as far as this test is concerned, because the test says if the limit is not 0, then the series diverges. But it doesn't say what to do if the limit is 0. So if the limit is 0, this test doesn't help us at all, and we have to try something else. Now, as it turns out, this series actually does diverge, and we'll see that with the next test. This series does diverge. It's called the harmonic series. It's a very famous example of a divergent series. One more quick example with this. Let's say we have the sum from n equals 10 to positive infinity, that's a plus infinity, of 1 over n to the 4th. Well, here, we want to take the limit as n goes to infinity of a sub n. What's our a sub n? Well, it's just this guy right here, 1 over n to the 4th. So this is the limit as n goes to positive infinity of 1 over n to the 4th, which is also 0, right? So as n goes to infinity, 1 divided by n to the 4th goes to 0 pretty quickly, okay? So again, the nth term test doesn't help us at all in this case, because remember, the nth term test says if the limit of the sequence is not 0, then you can conclude that the series diverges, okay? And here we see that the limit of the sequence is 0, so the nth term test doesn't help us. And just as a side note, this series actually does converge. So the reason I wanted to do these two examples here is I just wanted to point out that if the limit of the sequence is 0, then you might have a divergent series or you might have a convergent series. You'll have to do another test to figure out what's happening. But if you find that the limit of the sequence is not 0, then right away you can say, okay, the whole series diverges. One other thing to point out real quick, I started this series at n equals 10 instead of 1. And that doesn't matter. You can actually start this series at any number, generally any positive number, sometimes 0 we also take, and it doesn't really matter. The results will still hold. And that's pretty much true of every test for divergence. Because when we deal with sequences and series, what we really only care about is what's happening as n goes to infinity. Okay, so it doesn't really matter where we start because all the interesting stuff is happening as we go off to infinity. So this could be 1 right here, it could be 10, it could be 10 billion, and so on. The results will still be the same. Okay, so that's enough for the nth term test. Let's move on to the next test, which is P-series test. So P-series, I guess, isn't really a test, it's actually just a special type of series. So a P-series is something like the sum from n equals 1, or whatever, to positive infinity of 1 over n to the p. Okay? And this series converges if p is strictly greater than 1. So p has to be strictly greater than 1. And this series diverges if p is less than or equal to 1, including if p is 0 or if p is a negative number. Okay? So that's pretty much all there is to using this, to evaluating p-series. And if we look back at page 1 here, we see that this and this, these are both special types of p-series, right? So let's go ahead and rewrite those. So the sum from n equals 1 to positive infinity of 1 over n, that's a p-series with p equals 1. And if p is equal to 1, okay, so we see here if p is less than or equal to 1, then the series diverges. So if p is 1, then the series is going to diverge. Okay? And the other one that we had was the sum from n equals 1 to positive infinity of 1 over n to the p, or sorry, 1 over n to the fourth. And this is also a p-series with p equals 4. And notice that 4 is greater than 1, so this series converges. So the p-series test is pretty simple to use. It actually might even be a little simpler than the nth term test, but the reason I said you should always try the nth term test first is because the nth term test applies for any type of series, no matter what type of series it is. But this p-series here, this is a very specific, special type of series. So not everything is a p-series. You're going to encounter many different types of series, most of which, in fact, will not be p-series. So just keep that in mind, and the nth term test really should be tried first. Okay, so we see that these two are p-series. Let's look at one more p-series. So let's say we have the sum from n equals 1 to positive infinity of 1 over n to the 1.0001. So this is a p-series with p equals 1.0001. So we look at our p-series test. Is p greater than 1, or is it less than or equal to 1? Well, we see p is 1.0001, and that is greater than 1, barely, but still it's greater than 1. So this series does converge. So that's pretty much it for p-series. And the next test that I want to talk about is the limit comparison test. So a lot of stuff going on here. But using this test is actually not too bad. It's just kind of verbose when we talk about what it actually says. So we have the sum from n equals 1 to positive infinity of a sub n, and the sum from n equals 1 to positive infinity of b sub n. And the terms here, a sub n and b sub n, they're greater than or equal to 0 for all n greater than capital N. So what am I saying here when I say n greater than capital N? What I really mean is that all the terms a sub n and b sub n are all positive after a certain point. So remember on page 1, we talked about starting a series at n equals 10 because it doesn't matter where we start, all that matters is what happens as we go off to infinity. Well, it's the exact same principle here. Okay, it doesn't matter if finitely many terms in the beginning are 0 or negative. All that matters is that as we go off to infinity, eventually everything is going to be positive or 0. Okay, so that's really what this is saying, is that this test applies as long as eventually for some, or for little n greater than some big N, as long as eventually you have that everything is greater than or equal to 0. Okay, so now continuing with the limit comparison test, let C equal the limit as n goes to infinity of a sub n divided by b sub n. if c is greater than 0, then the series sum from n equals 1 to infinity of a sub n and sum from n equals 1 to infinity of b sub n either both converge or they both diverge. So basically what we do with the limit comparison test is we look at the limit as n goes to infinity of a sub n divided by b sub n. So we look at the sequences. We take the sequence a sub n divided by the sequence b sub n, take the limit of that as n goes to infinity. And if the result of that is positive, then the series do the same thing. They either both converge or they both diverge. Okay? So I want to point out that if c ends up being positive infinity, that doesn't count, because when we say c greater than 0, c has to be a real number. So if c is 0, or if c is positive infinity, then actually the test is inconclusive and you'll have to do something else. But if c is a real number, so not positive infinity, if c is a real number and positive, which it would have to be because of these conditions here, then the series both converge or both diverge. So enough chit chat, let's see an example. So let's say we want to test this series, n equals 1 to plus infinity, the sum of that, 1 over n squared plus 1. Okay, so this sort of almost kind of looks like a p series, right? Because we have a 1 over n to the p with p equals 2, but this plus 1 right here is kind of ruining that for us. Okay. However, we can think about the limit comparison test, and we could say, okay, well, this series really does kind of sort of look a lot like the sum from n equals 1 to infinity of 1 over n squared. So we can do the limit comparison test where this right here, 1 over n squared plus 1, is going to be our a sub n, okay, because this is the series that we want to test for convergence or divergence right here. This is the series we want to test. So what that means then is this is our a sub n. And again, we said, okay, well, it kind of looks like that p series, the sum from n equals 1 to infinity of 1 over n squared. So let me use this p series, and then this right here is going to be our b sub n. So the 1 over n squared is our b sub n. Now, why do we choose this? Because again, this series looks a lot like this series, and this series we can easily analyze. This is a p series with p equals 2, which is greater than 1, so this series converges. So the series converges. Okay, so this entire series converges. So if we do the limit comparison test with 1 over n squared plus 1 as our a sub n, so that says n squared plus 1, and 1 over n squared as our b sub n, well, let's go ahead and do the limit comparison test with that and see if we get anything useful. So start a new page here. So again, a sub n is 1 over n squared plus 1, and b sub n is 1 over n squared. Oops. So what we want to do is evaluate the limit as n goes to positive infinity of a sub n over b sub n, which is the limit as n goes to positive infinity of 1 over n squared plus 1 divided by 1 over n squared. Okay, so this is a sub n up here, and this is b sub n down here. So let's simplify that. This is the limit as n goes to positive infinity of, so here, if we divide by 1 over n squared, we're really multiplying by n squared. So this is the same thing as 1 over n squared plus 1 times n squared. So we're taking the limit as n goes to infinity of that. And we can write this more compactly as the limit as n goes to infinity of n squared divided by n squared plus 1. Now, what do we do here? Well, here, notice we have n squared on top, n squared on bottom, and we're sending n to infinity. So if you think about your Calculus 1 techniques, you can see that, okay, I have the degree on the top is 2, the degree on the bottom is 2, so the degree on the top and the bottom are the same, so I look at the leading coefficients, which they're both 1 on top and 1 on bottom, so they're both 1. So the limit is going to be 1 divided by 1, which is just 1. Okay, so the limit as n goes to infinity of a sub n over b sub n is equal to 1. Therefore, well, 1 is greater than 0, right? So the limit comparison test tells us that the sum from n equals 1 to infinity of 1 over n squared plus 1 and the sum from n equals 1 to infinity of 1 over n squared, that's an n squared right here. These series either both converge or they both diverge. That's what the limit comparison test tells us, because we ended up with this limit as n goes to infinity of a sub n over b sub n equals 1, which is greater than 0. Therefore, the limit comparison test tells us that these series both converge or both diverge, and we already know that this series converges. Therefore, this series must also converge. Okay, so that's an example of using the limit comparison test. So it might seem like this was really complicated, but actually it wasn't. I just wanted to go over a lot of the details with you and explain what the limit comparison test actually says. But when you're using this in practice, it really doesn't take that long. So all we really have to do is evaluate this limit and see, oh, okay, I get something, a real number, a finite real number that's positive. So the original series I want to test and my second series that I chose either both converge or both diverge, and the second series that you choose needs to be one that you can more easily analyze. Okay, so that's an example of using the limit comparison test along with P series and the nth term test for divergence. So I hope you found this video helpful, and thank you for watching.